Okay, perhaps you've heard tubes described as triodes or pentodes. Those are two common tubes we have in our industry. Most preamp tubes like 12AX7s are a dual triode. That's actually two triode tubes sealed in one little bottle. A pentode tube is a power tube. It's got one basic function in that tube, one tube, and it's 5 components as opposed to 3. A triode being 3, a pentode being 5. To basically understand a tube, I'm going to just give you the basics of a triode real quickly, then we'll fill in with the pentode, and we'll talk about preamp tubes and power tubes. But you need basically 3 parts to make a audio tube, and the first part would be essentially a filament, might also be called a cathode, and essentially this is our source of generating electrons. A good way to think about a tube, in fact in England they call it a valve. It's a controlled engine where you're controlling electron movement, and through that process those electrons create an amplitude. So I'll give you that as we go, but think of it as like an engine, and this is the source of the energy. Call it a gas tank, and it's usually a little very small tube. And we're going to show you a cathode here in a close-up so you can see how physically small. It's quite small, even in a 6L6. And in that tube, there is essentially a filamentary wire, which would be much like what you have with a light bulb. And we put a voltage on that, and we heat that up much like a light bulb. And this is what's called an indirectly heated design. Some tubes actually use the filament as the emitter, but for more efficiency they found years ago if you make your cathode nickel of a certain type, it will, and then you get it hot, it will produce more electron energy than, let's say, just a filamentary wire. And so this combined becomes essentially the first part of a tube, that is the gas tank. And this is going to radiate out electrons from this in various directions, because what we're going to do is we're going to charge these electrons with a negative voltage. And what we're going to do over here on the outside of it, now this is usually what blocks the whole view of a tube, so I'm just going to use it a little like this. It surrounds the tube. It's called a plate. And if you look inside a glass, you're going to see a big gray area, usually a big little piece of steel, if it's big or little, whatever. It's going to basically cover this whole mechanism. And this is our plate over here. And we're going to positively charge our plate with a lot of voltage. Big voltage. Big over here. And of course over here, this is going to be small, that we're charging our filament with. And what we're going to do is create an attraction for these electrons, a lot like a magnetic attraction. If we've got a positive charge over here and a negatively charged electron, what we're going to do is we're going to draw these electrons over to the plate as an attracted male-female kind of thing. You can get that. Now, what we're going to do, and this is one part up here. This is our filament. This is our plate over here. The actual control function, or we're going to control this flow, is going to be done with a third part over here, which we're going to call the grid. And the grid is essentially our gas pedal. It's going to be a 2-pole affair. It's going to go around here, and we're going to wrap wires around this whole thing. And we're going to charge the grid with another voltage that will offset or neutralize this attraction when we tell it to. This is actually, on a power tube, you've often heard where we have a bias voltage. What we're talking about is controlling this grid so its potential is matched to the ability of the cathode filament to emit and the attraction of the plate to attract, and we're going to stop that from happening, essentially creating an idle condition on this engine. Let me just label these again so you'll remember these. Filament cathode in a 6L6 or a 12AX7, that's the way these tubes are made. That's the source of our electrons. The plate is the direction we want to send them. This is the goes in, this is the goes out. The grid controls that. That's our gas pedal. And the gas pedal basically is attached. The signal that we use to drive the grid that tells us go or stop is the positive voltage that's generated usually from your guitar pickup, which is some magnets with some electronic wire wrapped around them, a string that vibrates. And somebody found out a long time ago, if you take a magnetic field and wave a wire in front of it, you create a voltage. That positive voltage is going to get applied to our grid. Remember I said we adjust our bias voltage. It's kind of like an idle adjustment on this little engine. So when it's all adjusted correctly with no signal, this is not emitting any electrons. We have a cloud of electrons forming in there, but they're held in containment by the grid. Now, when we apply a positive voltage to this negatively charged, negatively supplied grid, it lowers that negative supply and allows the beginning of some flow of electrons to go to the plate. So as we play guitar soft, we open it a little bit. If we play hard, we open it a lot. And the signal of our guitar is applied into this field. Well, the electrons that pass through that pick up that signal. They apply it over here to our plate, and our plate has a whole lot of voltage. Remember, we've got big voltage over there. For instance, our filamentary voltage over here may be 12 volts. In fact, a 12AX7 is what that means. A 6L6 has a 6-volt filament. A 12AX7 has a 12-volt filament, which, by the way, is split into dual triodes to be 2 6s, but I'm not going to get technical, but small voltages. And not a lot of current, not a lot of power. Over here we have a lot of current, a lot of power. That's where all the power comes from, is the plate supply. But when we've deposited our electrons over here and they've kind of mixed up with the electrons that are over here on the plate, we've got a whole big amount of power that has a characteristic of your guitar string attached to it. This little teeny positive voltage that came out of your guitar, not enough to drive a set of headphones, is now going to come out here. It's going to drive a 15-inch speaker. That's the process. That's the goes in and the goes out of this beautiful little 3-part engine that is a triode. And now that you understand the basic workings of this very simple 3-part machine, I can tell you this is actually called a triode. And if you look at a 12AX7 broken away, which I think I have a little sample of here, we're going to show you this to you in a little bit of a close-up. Here you're going to see two little plates inside of this little mica construction. It's going to be sealed in a bottle. At any rate, this is a dual triode. Now, a power tube would be more like a pentode. We're going to show you a pentode here in the close-ups. You're going to see a pentode. The pentode is just really a refined triode. There's really no more important devices in there, only efficiency devices. The easiest way I can understand, if I'm a voice and I want to be louder, I cup my hands and I'm louder. I've focused more energy. And what a pentode does, looking top down, this being filament cathode, this being our grid that's surrounding that, and this being our plate, which is usually 2 pieces of metal that are seamed like this. What we're going to do, here's our plate, here's our grid, this is called G1. With a pentode, we're going to use perhaps a G2, perhaps actually a beam forming device like this. And what we're going to do is focus this activity to go this way. Instead of randomly hitting the plate on all places, we're going to focus that activity. And in doing so there's 5 parts to that, and 2 are added to the triode to basically give us more efficiency. It's more focus. And it's usually designed for a higher power stage, as in the power stage of an amplifier, whereas a triode are typically used in the lower part preamp section of an amplifier. A dual triode 12AX7, a single pentode 6L6. This could be a 6L6 over here, for example. So those are the 2 types of tubes. Now, understanding that, we're going to move on and talk about why these tubes are different one from another, the way that we measure and match them that's meaningful for you. That's our next segment. Now that we understand a little bit how a tube works and what the basic components are, I think what we need to talk about is why they're different one from another, why we even match in the first place, why we can't make them perfect the same way every time. For instance, in stamping out cookies or something like that. It's a little more complicated than stamping out a cookie. Although the the ingredients of the cookie are very important, like a tube. At the end of the day, these are hand assembled. And we're working with, as we spoke about electrons, you can imagine we're influencing electrons here. So if one tube processes that electron a little different than another tube, it's going to have a corresponding difference in the way the tube works in your amplifier. Again, your amplifier is not a playback system, it's a producing system. Unlike playing back a record, you're actually making a record. So it's part of the production process, and therefore it contributes to the sound greatly. If you can't agree that the tube amplifier, or let's just call it the guitar amplifier, isn't at least one half of electric guitar, then we really can't move forward in this conversation. The amplifier is at least half of the sound of electric guitar and amp combination. And so we know that amps will sound different, guitars sound different, woods sound different, different kinds of materials on strings sound different. So you can pretty much imagine the tubes sound different. The difference is you can put your hand on a set of strings, you can put your hand on a pickup or a speaker. You can't put your hand on an electron because they're really small. Based on a comparison, imagine that this little electron that starts in the filament cathode area is going to travel over to the plate. While that may only be, I've got an actual tube here where we can see, this is the mica, incidentally, the insulators that hold all these components together in some perfect way. They're stamped perfect every time. But the components that go into those micas that hold them at these pre-assigned distances, which create the design of a 6L6 or an EL34, one from another being different. That's the design of these components and the way they're held in place. They're held in place by actually naturally occurring mineral mica that we farm, and we slice it real thin and we stamp it, and it holds all this tube apart. But imagine that the distance between the center of the tube and the outer plate, in this case, could be as much as an inch or a half an inch. And if you're an electron, that'd be like going from here to Denver. Okay, you're a small little thing. That's a massive amount of area and distance to negotiate and travel. Along the way, you're going to be bouncing around and knocking with all your other electrons, and that's going to influence your travel. So there's a lot of variables in the way we punch and put these things together. At the end of the day, tubes are still handmade. There's no way to produce this finished product on a machine. It's all done by hand. We can stamp the parts. We can make sure those are very consistent. They typically are. But we have to hand assemble it. A lot like Martin guitars are hand assembled from parts, and they're not all identical. But to a much bigger degree, because of the size of the electron, the thing we're basically influencing, and the world that lives in, the physical size of the tube could be the size of the United States. In one tube, when this was hand assembled, the grid could be in Denver, and another tube it could be in Kansas City. And so applying the same voltages everywhere doesn't necessarily mean you're going to get the same result out the other end of the plate. This is what creates the differences. So if you could imagine the cathode in that center rotating out to the plate, in this case being formed by our beam former to focus those to our side point here, then you can imagine the differences in these geographical locations can create a different efficiency to the tube, a different end result. And just to follow up a thought I might have missed earlier, in case you didn't know this, and I should make this blatantly obvious, this is where the guitar signal comes in, this is where it gets amplified. The plate is connected in a guitar amplifier to an output transformer that's unique to tube amps. Transistor amps don't have them, that's why they're lighter. They've only got one transformer which creates these voltages. But a tube requires an impedance matching device between it and its speaker over here. Speaker. So to finish that thought, the electrons exit very high voltage, go through a transformer, converts that to the right impedance, let's call it 8 ohms, and that's where our energy comes out of our speaker. But when you're hand assembling these things, one to another, these variations must occur. It's the nature of it. You can't make two snowflakes the same, and we certainly can't make two tubes the same. So that's why they're different. Now we're going to talk about what those differences mean, how in the past we've measured those differences, and how groove tubes basically discarded those old test regimes and developed new ones. Okay, testing regimens for tubes. I think when we're talking about matching tubes, we're really leaving out a word there. We're matching power tubes. Preamp tubes don't need to be matched. We'll talk about preamp tubes in a separate section. So we're talking about matching power tubes here. Power tubes are very often, if not always, used in a system that has 2 or 4 tubes. For instance, a 50-watt Marshall has 2 EL34s, a 100-watt has 4 EL34s. So we're talking about how to get those 4 tubes to respond to your touch, your play, and have a similar sounding result so that they all are playing sort of in harmony. It'd be a lot like a band all singing in the same key, if you will. That's why we measure and match power tubes. Now, in that we're calling them power tubes, it might be a no-brainer to say, well, let's just measure power. That's a great idea. And that, of course, is what systems we started to do 25 years ago. We took the standard RCA measuring systems. We took a lead from Macintosh amplifiers that were measuring those Macintosh amps for your hi-fi amps and supplying you factory-matched tubes. And we just took a page right out of the tube book and said, here's how you match tubes. Let's say this is a 6L6 for a minute that we're going to measure and match. Well, 6L6 is basically a 20-watt tube. That means maximum power, 20 watts. Of course, that starts down here with no signal, and that's 0 watts. So what happens, and it's true, that many tubes, if you measure just the power, and that essentially means you open the grid wide up, you let it produce as much power it can do, and you measure the power over here at the plate. So everything else being equal, how much does this 6L6 produce? And you will get differences. You'll find that some will actually produce 22 watts in those circumstances. Others, right on the target, 20. Some may be down here at 18 watts. You know, and these are differences that you can measure. And if you'll recall, I gave you a statement earlier that I think I live my life by. There's things that you can measure that don't matter. Here's one of them. It doesn't matter because we can't hear small differences in power. If you know much about how acoustics work, it takes almost double the power to hear a noticeable difference. A good example I can give you in the music world is that a 100-watt Marshall isn't twice as loud as a 50-watt Marshall. In fact, I've heard some 50-watt Marshalls that sound louder than 100-watt Marshalls if they're not set up correctly. But point being is our ears are logarithmic, and the technical explanation is it takes double the power to hear 3 decibels of difference. 3 decibels is not very much. Look on any volume control on a console and move it 3 dBs. It's only a noticeable difference. So if double the power is just barely noticeable, then small differences, which would even be called 10% at a wide range, aren't very noticeable to our ears. So here's something that we can measure, and I can give you 2 tubes that put out 18 watts, 2 tubes that put out 22 watts. But it won't mean anything. And of course, when we started Groove Tubes, I think I told you, we tried this, and we couldn't hear any difference. So I knew one thing after working in the music business all that time: if what I'm going to sell you doesn't make a difference in your life, doesn't improve your instrument, doesn't make you sound better or more musical, I'm just selling snake oil. And that wasn't my goal. My goal was to try to make a contribution, a meaningful contribution. I wanted to make that magic Marshall for you out of your amplifier, which is a normal Marshall. And so that's really what the process was about, and we weren't accomplishing it with this. And I thought at this point, frankly, that my great idea was a bust. It wasn't going to work. However, we standed back and we started, remember I told you, there's things that matter that you can't measure. So we decided to start finding some of those things that mattered, that could be measured, and we came up with some really interesting, very interesting approaches. Let me tell you how the thought process worked. Again, I told you, we don't use these as electron devices. We're using them really as tone generators. If we wanted electron devices, we'd use a transistor. They're far cheaper. They don't require that output transformer. They require less power from the wall. They're the modern device. I mean, transistors were supposed to basically eliminate tubes, and they did in every consumer aspect you can think of. There's very few tubes used anymore except for military, avionics, and our world. You know, we're still back on the tail end of technology because we know as musicians tubes sound better. And until they come up with something that sounds and feels and as natural as a tube, we're still going to be using them, which is why we're still growing after 25 years. But we don't use them as electron devices, but as tone generators. Again, part of the production process. So let's talk about what we can measure that we can hear that might make a difference. And now we're going to start talking about THD. Broken down, that means total harmonic distortion. Now, I guess distortion is one of the key words here. To measure distortion, give you an example. If you look at a specification on your hi-fi gear at home or your Sony Walkman, the distortion is 0.000 something. But of course in guitar amps, we commonly turn amps up until they distort. as part of the production process. And we're very interested in that process of distortion, because even 1% distortion is audible, 2 or 3% quite audible, whereas 10 or 15 or even 50% or 100% in power differences isn't audible. Small differences of distortion are. So that was interesting to us. Let's start looking at how a tube distorts in a dynamic sense as it goes from no power to full power, how it distorts. And this is the heart